recording this. Well, I'm sorry, Ruben. All right. I'll start recording it now. All right, so let's look at an example. A light wave traveling in the air strikes a piece of glass. The frequency of the incident wave is 5.1 times 10 to the 14 hertz. Angle of incidence is 30 degrees. Angle of refraction is 20 degrees. So in part A, it says find the angle of refraction of or index of refraction of the glass. So how do we do that? Oh, no, first it says find the speed of light in glass. So how do we find the speed of light in, no, find the index of refraction of the glass. Find the speed of light in the glass is fine too. Okay, so how do we find the speed of light in glass?
Well, we can take the fact that the angle changes and then use that to find out how much n will change. And then n equals the speed of light over the velocity.
Okay, so here we go. Maybe it makes more sense to find the index of refraction first. Okay, so let's find the index of refraction first. We know n sub 1 sine theta sub 1 equals n sub 2 sine theta sub 2. One thing you ought to know is that n for air is what? One. Air is what we typically see the most. It's what we look at. It's the thing that's not distorted for our eyes, right? So index of refraction for air is 1. You should just know that. It's easy. It's like knowing what atmospheric pressure is. 1 atmosphere, right? For our air. Okay? So, n sub 1 is 1 times the sine of incident wave. Angle of incidence is 30 degrees, so sine of 30 degrees equals n sub 2 sine of 20 degrees. So we know it's going from a slower medium to or from a faster medium to a slower medium, don't we? How do I know it's going from faster to slower? Yeah, because the angle decreased. Yep. So what is n sub 2? Okay, so 1.46 is the angle of, or is the index of refraction of glass.
Yeah, what's the units?
There are no units. No units.
Yeah, because velocity.
Mm-hmm.
So it's like a physical gravity.
Yep, there are no units for index of refraction. It's just a number. There you go. That'll be yours. All right, so let's go back to A. Find the speed of light in the glass. What did we just realize? We said we defined n as being c over v, didn't we? Well, we know what n sub 2 is. So now we can figure it out, can't we? So v sub 2 is going to be c over n sub 2. So let's figure out what that is. 3 times 10 to the 8th divided by 1.46, which means it is going to slow it down, isn't it? Well, yeah. It's not going to change it that much. What is it? 2 point what? 2.8, I bet. Yep. Find the frequency and the wavelength of refracted light wave. So what do we know about frequency and wavelength? Frequency doesn't change, guys. Wavelength changes. Frequency doesn't change. Frequency is frequency for something. So the frequency in the medium is the same as the frequency in the air. Think about that. So it is still what? 5.1 times 10 to the... Guys, frequency is what we use for what? Like, would you agree? Wouldn't that be awful if it did change based on the medium? It would change from going, the radio waves leaving the tower for your favorite song, and then it has to float through the air, through all kinds of things, and the glass and your walls and everything in your house. If it changed when it went through all those different medium, what would you be hearing?
Probably weird static.
Mm-hmm.
Well, isn't frequency
No, it's
What?
frequency.
Frequency? We've got there's an inverse relationship between wavelength and frequency. As one goes up, the other goes
So shouldn't that be
down.
like wavelength also? That be okay.
No, because the speed changed. Remember, here's the key to this. What do we know about velocity? It is frequency times wavelength, isn't it? We learned that last time. Frequency times wavelength. So if the velocity changes but the frequency stays the same, then the wavelength had to change, didn't it? Frequency and period are inverses of each other. So if the frequency doesn't change, the period doesn't change. But the period is not the wavelength. Frequency is the number of cycles per second. Oh yeah, he does. They're over there. Did you get the one with the color from over there? That's what you need. That's that one. And I gave it to you in color this time because it's got the wavelength chart on it. There's some things you need to see in color. So are we good so far? So what do we know? V sub 2 equals F wavelength sub 2. So now all we have to do is plug in, don't we? 2.05 times 10 to the 8th equals 5.1 times 10 to the 14th times the wavelength. So how does the wavelength change? This also explains why, when we looked at the 3 different colors of light, why they all bent differently. Why some of them had a different critical angle than others did. It's not just the position of the color, it's the wavelength of the color, right? As the wavelength of the color, think about it. The wavelength of the color changes the velocity going through, because the frequency is not going to change for white light, but frequency is not going to change at all for the white light. It's just going to change for the wavelength will change for the different colors. This is why a prism works. Think about what a prism does. Prism takes a beam of white light and it separates it into its component wavelengths, doesn't it? Why is that? Because each one of them has a different wavelength. The different colors have different wavelengths, which means what? That they change velocities differently as they go through the same medium. If they have different velocities, they end up with different spread, different angles, different refracted angles, don't they? So what happens? they spread out, okay? So what we have is that white light going into the prism and then fanning out because it's all bending differently because it's got all different wavelengths. Huh? Yeah. We did that last time. If you look at it, here, you didn't get a chance to see this, but we have it. Absolutely it does. If you look at this chart, you can see, here we've got, and here's the frequency, here's the wavelength. So here is our different colors, and you'll notice that the higher wavelengths, right? The higher wavelengths go towards red. Blues and indigos have the lower wavelengths in the visible spectrum. So yeah, different things have different wavelengths. It's actually inverse of the frequencies. I mean, they're different. As one goes up, the other goes down because of this relationship right here. E is energy. Energy is Planck's constant times the frequency. We'll get to that. But yeah, it's in that other set of notes too. So, but yeah, you should look at. Yeah, you did have to do this. I see what you're saying. You did have to watch those.
Yeah, that's what
and look at it. So that's what you didn't do or did do?
No, that's what I did do.
Good, because there's some information, you really need to go watch those two, because there's some information in there that you're not gonna really cover. Yeah, they were like 5 minutes long each. I told you it would take more than like 30 minutes to watch. Yeah, it wasn't very long. No, I watched them all, and it took me like 30 minutes.
Yeah.
But there's some information in those that we're not gonna cover in class that you really do need to know. Okay? So, but anyway, so yeah, there is a difference there. Okay? Frequency has to do with like radio waves. Okay? That's the thing that gets them through. But there is a wavelength also. But really what we're concerned about, what wavelength is concerned more about, is this visual light spectrum. And this is why, notice they have different wavelengths. From here to here, they're not very different, but they are a little bit different from indigo all the way through to red. Okay? Well, I mean, radiation is here. Frequency, what I was telling them is frequency has to do with, wavelength doesn't have anything to do with energy. Frequency has to do with energy. The higher the frequency, the more energy it has, which is why things like infrared cooks your food, or potentially cooks your food, right? Like the microwave is what microwaves do, but anything above radio waves begins to be a little bit hazardous to humans if you're exposed to it too long. Like microwaves, you wouldn't want to put your stuff in the microwave. It would cook you. But those are really, for a while, right? But you can be exposed to them just a little bit, like for an x-ray, this is not x-rays, at the, like if they're scanning you for like guns and stuff at the airport, metal detectors are in the temperature, but you barely, I mean, it's just a blink of walking through. Infrared, like for your remote control. Now, you get up past the visible light spectrum and it really becomes hazardous. This is hazardous. Ultraviolet burns you. That's your sunburn. X-rays, of course, too much exposure to X-rays is going to cause cancer and burning. And then you get all the way up to the highest, which is gamma rays, which if you even have very little exposure to gamma rays is going to make your cells cook and explode and degrade. And yeah, this is your nuclear radiation up here. So it takes minuscule amounts of this to really mess you up. The lower the frequency gets, the more exposure you can have without anything bad happening because the energy is so low. Really, 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 really high energy, high frequency means really, really high energy, which of course is bad for you. Make sense? Okay, so let's keep going here. So, person stands, did we figure out what that was?
It was 4.02 e to the negative 7.
2.05. Okay. To the 8th divided by 5.1 what? Was it 5.1? Is 5.1? Yep, 4.02. Times 10 to the negative 7th And that is what? Wavelength is in meters. Okay? Frequencies in hertz. All right, so let's look at example B. A 2-meter tall person, this should say a 2-meter tall person, stands at the edge of a pool that's 10 meters wide, that's 3 meters deep. The person looks at the center of the water surface and sees a coin on the bottom of the pool. What's the actual location of the coin? So how do we figure this out? Obviously, he can't just look straight at the coin, can he? He thinks he is, but light's really, where does he think it probably is versus where it actually is? It's weird, isn't it? So this is going to be, here's theta. There's the 1, right? This is the angle of what? Incidence. And this is the angle of refraction, correct? So we know it's somewhere x. That's what this is. It says 5 meters until he looks at it. Okay? Center of the water surface. How do I know the center of the water surface? Because it tells me the pool is 10 meters wide. So this is the center. So he looks 5 meters, and then it is some distance past that, isn't it? Okay, so let's figure out what, first thing we got to do is figure out what? So what do we have? We know N for air is 1. And N for water is 1.33. In case you didn't know, that was 1. We do know that. For light and water is 1.33. So we can figure out what? First thing we got to do is figure out what the doggone angle is he's looking in on it at, don't we? Okay. Good old trig. So let's figure out what we got here. Let's pick a different color here. We have a right triangle right here, don't we? And we know this is 5 and this is 2 because he's 2 meters tall. So to find theta 1, we know that tangent, theta sub 1, because it's opposite over adjacent, right? 5 over 2. So theta sub 1 is inverse tangent of 2.5, right? So what's the inverse tangent of 2.5? (68 degrees). Found 68 degrees, okay? Now, we can find the angle of incidence using Snell's law. So we know N sub 1 sine theta sub 1 equals N sub 2 sine theta sub 2, correct? Well, we know all of those, don't we? 1 times the sine of 68 degrees equals 1.33 times the sine of theta sub 2. Okay? This is a 3-phase problem, guys. Because remember, what we're really trying to find here is this chunk right there. Do you see where I'm headed with this? I know this is 3 meters. I'm going to fix it to have this angle right here. I know this is a right angle, and I'm going to go, I went trig to find the one angle. I'm using Snell's law to find the second angle, and then I'm going to go back to trig again to find that distance. So what is theta sub 2? It's the inverse sine, right, of the sine of 68 degrees divided by 1.33. Okay, so 44 degrees. And now finally, we'll go to this right triangle again, where we now know this is 44 degrees, and we know this is 3 meters, and we're looking for x, right? So that's tangent again, isn't it? Tangent of 44 degrees is equal to opposite over adjacent. So x is 3 tan 44, which is what?
$2.9.
2.9. Now, what's the actual location of the coin? That's not the actual location of the coin, is it? That's just this. Let's answer the actual question. Location of coin is going to be the 5 plus the 2.9, isn't it? Location of the coin is here. So that would be what? 7.9 meters from the edge? From the edge of the pool. Okay? Right? That's a pretty typical Snell's law type problem. Okay? Now, any questions about that one? Let's look at light traveling through a vacuum when it encounters a 1.1 meter thick transparent material with n equals 1.5. Calculate how far the light is displaced. In other words, guys, what's going to happen is it's going to go from 1 to 1.5. So what is it going to do here in this picture? It is going to bend towards the normal, isn't it? But now it's going back towards a what? It's going from a slower to a faster. So now it's going to bend away from the normal again, isn't it? So as a matter of fact, it's going to bend back like the way it came in. Make sense? So if we were to extend this line straight out, it should be parallel to this other line, shouldn't it? Should these two not be parallel to each other? Yes, it should. So it's asking how far is the light displaced? What it's asking for is this. What is this distance right here? That's how far the light's displaced, isn't it? This is a complicated problem, but it's not impossible. So now we got to figure out what's going on here. Let's take this one step at a time. So let's take step one, which is let's figure out how much it was moved. Okay? So I'm going to look at this and I'm going to draw this picture again so I can do a little bit of figuring out what I need to do. So I've got this and I got this and I got it coming in here. Going this way. Got another normal, don't I? And now it's bending back that way. So I have theta sub 1. And guess what? This is also theta sub 1, isn't it? This is why things don't distort when light goes through your window. Why you don't see things weird. This is why when you look out this glass right here, stuff doesn't look out of place, does it? because the light's coming in this glass, refracting while it's in the glass pane, and then bending back to the way it was before it hit the glass, coming to your eye. Okay? However, underwater, things do look different if you're looking from the water up or if you're looking from up into the water. If it doesn't pass back out of the medium, it stays refracted and in the wrong place, doesn't it? So, how do we do this? We know this is 0.1 meters, don't we? This is theta sub 2. Okay? If that is theta sub 2 right here, then by alternate interior angles, that is also theta sub 2. Do you agree? Now, I need you to know that because now I'm going to draw on the other chunk. This guy right here is parallel, correct? So what I want you to notice is two things. Number one, I have this triangle right here, which is a right triangle. Then I have this triangle, which is also a right triangle, correct? Now, that's not what I'm trying to find. What I'm trying to find is this. I'm trying to find this distance D right here. But, do you see how knowing those two triangles is going to help me with that one? I want you to think about it. If I know either this angle or this angle, which I can know, and I know this distance right here, then I have another right triangle, don't I? And I can find that little distance. So let's take this by the numbers and figure out what all this is, okay? Now, did it tell us how far? Oh, it did. It gave us 30 degrees right here. So we know this is 30 degrees coming in. What we need to find is theta sub 2, don't we? All right, so let's start with Snell's law and find theta sub 2. N sub 1 sine theta sub 1 equals N sub 2 sine theta sub 2. Coming in from air, right? Through 1, and then 1.5. So 1 sine 30 equals 1.5 sine theta sub 2. So figure out what theta sub 2 is for me. Inverse sine of 30 divided by 1.5, right? So what? Okay, so about 19 degrees. Okay, so this is about 19 degrees. Close enough. Now, that helps me. Because here's the thing. And let's look at some information here. I'm going to go with this. I've got one triangle, the green one that I highlighted. The green triangle is here. I know this is 0.1, and I know this is 19 degrees, and I want to find this. I'm going to call it X. Okay, so this chunk right here is X. So let's find that. This is tangent, isn't it? Tangent of 19 degrees is opposite over adjacent. So what is X? .034, yeah. Now, let's do the other triangle. That's this angle right here, isn't it? Do you guys see that this angle and this angle are the same? Aren't these vertical angles? There's a lot of geometry in optics. So theta sub 1 was 30 degrees, wasn't it? So this is also 30 degrees. This is still 0.1. And we are looking for this, y. This right here is y. Okay? Right angle here. So let's find y. So y is going to be tan 30 times 0.01. So 0.058. Okay? So now if I want to find this little chunk right here, that little chunk right there is y minus x, isn't it? So y minus x would be 0.058 minus 0.034. And that is 0.024. All right. So now we have to figure out what this angle, one of these angles is. So if I can find this angle right here, if I know what this angle right here is, then guess what? I know what that angle right there is, don't I? Yes? Okay. So
180 minus 69.
yep, because this was 30 degrees, this was 90 degrees, so this has to be
30. No, the one at the top.
yeah, this is 30 up here.
No, that's 60.
No, it isn't.
Yeah.
It's 30.
That's 60.
No.
Because if you look on top of that, there's the
Yeah.
30 underneath.
30 here.
That's not 30, it's 60.
This is 30.
This 60. You see it?
Walk up and show me what you're saying.
30. 30 up here.
No.
Since they're parallel, doesn't that have to be 30? Or is the
It reflects out at the same angle it reflects in.
okay.
If this is 30, then this is also 30.
Okay.
Because remember, it's always measured from the normal.
Okay, that does make sense.
Well, I mean, it looks like 45 in the picture, but, you know, there's no counting for art. It is 30. The picture is not to scale. Picture is not to scale. So that's 30. So we good with 30? Right there? So if this is 30 in blue, then this is 30 also, isn't it? If this is 30 and this is 90, then this has to be 60, doesn't it? The picture is way not to scale. Okay?
Yeah.
All right. If that's 60, then guess what? This is 60, which means the other is 30, isn't it? Because 90 degrees. All right, so this is, now we've got a triangle. Where we have 60-degree angle here, correct?
Yeah.
We know the hypotenuse is, and we are looking for D. Mm-hmm. 0.02, right? Now, I'm going to show you a shortcut that I've yet to figure out. Maybe you can figure out the geometry of it. I just haven't sat down to figure out why it works, but it works. If we do D times the cosine of the angle of refraction, we get 0.1, which is the width of the material, right? Times the cosine of 90 minus theta sub 1 plus theta sub 2. And this is the width of the material. But you'd have to know that by heart. I'd rather just follow the geometry, honestly. Well, you still get 0.02. It works out, but dang. All right, total internal reflection. Here we go. This is what we're talking about, total internal reflection. This is that critical angle that we were talking about. Incident angle that results in an angle of refraction of 90 degrees. If the angle of refraction is 90 degrees, guys, that means what? As it comes in, okay? If it comes in, then what happens is it hits the barrier. Here's n sub 1, here's n sub 2. Theta sub 1 is here. Theta sub 2 is 90 degrees to this, which means it is literally here. That's 90 degrees. That's theta sub 2. So what does that mean? It means it doesn't reflect back out. It doesn't refract. It goes along the edge, doesn't it? That means it's total internal reflection. So we describe the critical angle as the incident angle. Angle of refraction of 90 degrees. If theta sub 1 is greater than theta sub c, which is the angle, critical angle, okay? So critical angle is theta sub c. No light escapes. So let's see what that looks like in Snell's law. How do we find the angle of critical angle? Think about it. N sub 1 sine theta sub c equals n sub 2 sine of 90. And what is sine of 90 degrees? 1, isn't it? So basically what we get is n sub 1 sine theta sub c equals n sub 2. Sine theta sub c equals n sub 2 divided by n sub 1. So theta sub c is the inverse sine of the ratio of the indexes of refraction. So we can find that critical angle for any two substances. We can find it for going from water to air if we needed to, or from air to water, etc., right? You good? So let's look at this question of Aquaman. Okay, sorry. All right, quick example. Aquaman is swimming underwater at a depth of 2 meters and looks upward. Explain why Aquaman can only see the world outside the water through a circle on the surface. Calculate the radius of the circle. And how will the answer change if he looks up from a deeper depth? I want you to think about why it's a circle. This is the what? If you can only see it looking through a circle, we've got a critical angle here, which means we also have a critical angle here. If we have a critical angle there, and he looks around himself at 360 degrees, anything greater than that critical angle is outside that circle, isn't it? In other words, this thing is kind of a circle on the surface, isn't it? Do you understand that? Anything outside that circle is greater than the angle of the critical angle, okay? So it looks like a circle of water on the surface. So in part A, all right, we will finish this up very quickly at the end or at the beginning of next class. We will talk about dispersion and look at white light through a prism. Okay. I need you to do as much of 6-2 as you can. I think it'll be pretty easy to do most of 6-2. We are going to do the Snell's Law lab next time, and then the time after we will start talking about mirrors and lenses, okay? There's a difference between a mirror and a lens. We're going to take a lot of time to look at mirrors and how mirrors work, and then we'll do look at some examples of reflections with mirrors versus getting into then the idea of lenses, geometric optical lenses. We're going to do a lab with lenses as well. All right, any questions on any of those? So 6-2 stuff. 6-2 exercises.